everyone, my name is Loubna. I work in the science team of HuggingFace. And today I'll walk you through a project that I've been involved in for the past year, and also a very hot topic in machine learning right now, which is code generation models. I hope this talk gives you some insights into these models and how we can leverage them. So before we get into the technical details, let's start with some context. I guess the first thing that pops in people's heads when you say code generation models is probably GitHub Copilot, which was the VS Code extension released by Microsoft 2 years ago, and it basically autocompletes your code, and it is based on a model called Codex released by OpenAI. So people were very excited about this Codex model because the models that were before it were not very great. For example, CodeGPT, bars, they were like kind of small models, a few 100 million parameters, and they were trained on very little data, so they were not as good at Codex on like just code completion. So what OpenAI did is they showed that you can just train your code models, like you do for your language models, take a very large language model and give it a lot of data, and it kind of learns how to generate code. So after that, DeepMind worked on AlphaCode, which is also a strong code model, more oriented towards competitive programming. And AWS also released Code Whisper. So very exciting things were happening in this field. Sadly, all these models which are strong are closed models. So you can use them either through an API or they're just not available for the public to use or test. So the open source community tried to develop and reproduce these models with models, for example, like CodeParrot from HuggingFace, Polycoder, Encoder, and CodeGen from Meta and Salesforce. So this is very great, but these are not the models I'm going to talk about today. I'm going to talk about how we're trying to address some open questions. So although we have these models, they were still not as good as Codex, especially when it comes to other languages than Python. And there was a lack of transparency about the training data that went into these models. For example, Encoder and CodeGen didn't release the data, it was just like a paper explaining how it was curated, and it was lacking a lot of details. So it was very hard to understand what really went into these models and how to reproduce them. There's also some open questions about like the evaluation of these models and reproducibility. So this was like the journey of the open source community, and let's see how HuggingFace is contributing to this field. So a year ago, we released CodeParrot, and one of my colleagues was actually in DataFest last year talking about this. So I'm very excited to be back talking about what we've done since then. So when Codex was released, there wasn't really a GitHub code dataset that people can use to train these models. There wasn't also a pipeline because this was kind of new for code models. So our goal with CodeParrot was to have like kind of an educational and a pipeline for people to reproduce this. So it wasn't more focused on performance. It has a 4% Python score, which is kind of low if you compare it to current models. But it was more like an educational pipeline. It was trained on permissive data, and it was open access. But since then, we've gotten more serious about training these models. And so a few months ago, we released StarCoder, which is a 15 billion code generation model trained on more than 80 plus programming languages. It was the strongest open source model for code generation. And just like CodeParrot, it was only trained on permissive data. Because on GitHub, you can have either permissive license or copyleft license, which is you can't really use that data without keeping that license, or no license. So for us, we only keep the permissive one. And the model is also open access. Today I'm going to try to talk about the BigCode community, which is where this model was developed, the data sets that we developed, the architecture of the model, how to evaluate it, and also deployment, which is missing. That's what happens when you update your slides last minute. What's BigCode? So BigCode is a collaboration between ServiceNow and HuggingFace. And the goal is to develop code models in an open approach and also responsible. And it's open for people to join. We had more than 500 participants from different organizations and companies from over 30 plus countries. And so we have a core team that's working on the project for a full time, but we also have external contributors helping with the project. And why did we decide to start BigCode? The purpose was to kind of address some of the concerns of closed models development that we see nowadays, where the training data and sources are not disclosed. So you can't really inspect what went into these models, and you can't easily reproduce it. The weights for the models are also not public. So if you want to use these models, you have to send your data, which must be sensitive, to an external API. You can't really deploy these models on premise. And you can't also fine-tune them. And yeah, needless to say, you can't reproduce if you don't have all these components. So what we think open large language models development should look like is to have the opposite of all of that. You should have a public data that people can inspect and maybe opt out if they don't want to be in your trainings. You should also release model weights and fine-tuning scripts to get people started, because this way people can build up on your work. This will also allow on-premise deployment so that people don't have to send their data to an external, a third party. And yeah, this should be fully documented so that you try to foster research. So that was the brief introduction. Now let's see how do you really train these models from scratch. Probably already know that it's like a lot of GPU hours, terabytes of data, but that's not all. And that's what I'm going to try to show you in the next few slides. So what I'm going to show you is like how we train Starcoder, our model. It's named after Star Wars. It was released on 4th of May. And so yeah, we spent more time arguing about the name than training. The most important component is the data. If we learned one thing is that we need more data, but we also need better data. For the more data part, I'm going to talk about the scaling laws. So let's say you have compute for training these models. You're not just going to blindly choose the model size and data size because you want to allocate this compute in an efficient and optimal way. To do that, we follow what's called the scaling laws that tell you if you have a fixed compute, how much should go into the model size and how much should go into like the training and the size of the data. So until 2020, we were following the top-line scaling laws from OpenAI, which basically say if you, for an amount of compute, I'm just going to give some random numbers, but like to illustrate this, model size is more important. So for example, if you have 10 times more compute, you have to put 10 times the model size, but just 2 times the data size. So there was a tendency to make models larger without actually making the data set larger. And this is why GPT-3 is like 175 billion parameters. Bloom is 170. OPT was also the same size. Yeah, so that was the trend before the chinchilla scaling laws came. And this is why now you find much smaller models. No one is actually training now dense transform models that are this size. Basically because DeepMind with their chinchilla laws found that you actually, the top-line scaling laws were not completely right. If you want to scale, you have more compute and you want to scale your model, you should proportionally scale your data. So 170 billion parameter models that's trained on 500 billion tokens is so much undertrained and you're really not using your compute well. So yeah, after that people started following the chinchilla scaling laws. So for example, for 60 billion parameters, they tell you that the optimal compute spot for using your resources is to train on 1.6 trillion tokens. So after that, yeah, that's kind of the scaling laws we started following. But then models like Llama came out, which, for example, the 7B billion parameter models, they trained this on 1 trillion tokens. If you look at the chinchilla scaling laws, they said that the 7B billion parameter models didn't need 1 trillion tokens. The sweet spot was much before that. So people were like, oh, why did they overtrain their models? Were the chinchilla scaling laws wrong? And that's not the case. It's just that people kind of misunderstood what the chinchilla was trying to say. Because compute optimal is like how to spend in an optimal way your training compute, but it doesn't look at inference. So if you just try to scale your model and have 60 billion parameters or 1 trillion token, that's going to be hard to serve in inference. So it's much better for you to take inference into account and go for a smaller model and you train it longer. And this way people, the community can train this on like less GPUs. You can also have it like easily deployed for inference. So yeah, compute optimal for training doesn't necessarily mean that your model is optimal. And so now people train much smaller models for much longer. For example, like the Llama model, which was trained for 1 trillion tokens. Now you can even find 1 billion tokens, which are trained for more than 500 billion like tokens on your data. It just works pretty well. The loss continues decreasing. It doesn't stop at like the chinchilla sweet spot. So now let's go to the other thing, which is like we covered the more data, now the better data. What kind of code goes into these models? So we started from the stack, which is an open source data set that we released, which has GitHub code. It has more than 6 terabytes of permissibly licensed data in more than 300 programming languages. It also has a data inspection tool and opt-out mechanism. What does this mean? You can basically go to this demo called Am I in the Stack, and you can type your GitHub username. It tells you if you have any of your repositories in our data. And if you want, you can opt out if you don't want to be included in future trainings. You just have to fill a form and we'll remove your data from the stack. So this was like a good starting point to have like a more ethical and responsible approach to developing these models. And so we started from the stack, but we actually trained on stakeholder data, which is Allal, which is a subset of the stack after some cleaning. And it has 800 gigabytes of code in 80 programming languages with GitHub issues, Jupyter notebooks, and Git commits as like external and new data sources. So where did the 6 terabytes go? This was one of our colleagues whenever we did the filtering. You would go with 1 terabyte and come back with a few gigabytes. So it all went in data curation. We basically tried to clean the data as much as we could. First, we didn't keep all the languages. There are some languages that are no longer used or maintained. And we also added like GitHub issues and the other sources as I previously said. And we also did a lot of quality inspection. Because for example, you want to remove auto-generated files, and for that you can use filters like the average line length, the percentage of alphanumeric characters. And these kind of filters are not language agnostic. So for example, I think JavaScript had like some files that has like long lines, and you shouldn't use the same value for all the languages. And sometimes you can have some outliers in some like languages. For example, we found there was like a lot of XML data in MATLAB. And so what we did was like take 100 samples per language and set up like a demo, and people manually looked through them. And if they found something weird, they kind of flagged it. So since we had the BigCode community where there are a lot of external contributors, they kind of helped with this data curation. So this way we were able to find like some custom thresholds for these filters for each language. The other filtering that we applied and that gave a huge performance boost, that is language agnostic, is deduplication. So in the stack, you can't find like a file that's completely the same, exact to another file, because we already did the exact deduplication and we're scraping the data. But you can still find files that are called near duplicates, so they are similar but they're not exactly the same. For example, two functions that use different variable names, they're still doing the same thing, but if you just do exact matching, you're not gonna remove one of them. So we do some near deduplication where we try to remove these files that are kind of similar. Because there were studies for language models that show that duplication really hurts model performance. And the larger the model gets, the more critical this is, and the more your performance will be impacted. And we did some experiments to see if this holds for code data sets, and we found, yeah, that like removing near duplicates really boosts performance. Here you can see like some examples. What's involved is like after near duplication, it's always better than not doing the duplication. And this filter is great because it doesn't depend on the programming language, so we just launched it on our programming languages at the same time. And for the algorithm, it uses something called min hashing to kind of represent each string in like a set of numbers, and then it uses LSH to kind of create clusters, and then inside those clusters you decide which files stay and which files get dropped. Okay, so that was for duplication. Then we removed personal identifiable information because you don't want your model to memorize people's SSH keys and API keys who are in GitHub. And yeah, we trained like a named entity recognition model on the data that we annotated. And yeah, we used it to kind of mask all these entities from the data sets. And we also did data decontamination. I think Augustine talked about it this morning, but like it's very important that like your test sets and validation sets don't have what like you trained on. So for example, there's this benchmark called human eval, and it turned out like some people put it on GitHub, so we kind of scraped it. So it was very important to remove these test benchmarks from the training. So that was it for curation. We also did some formatting for the data. For example, at the header of each file, we added the repo name, the file name, and the number of stars, hoping that during inference you could maybe use them to say this file is, for example, solution.py. The model will know it's a Python file. You can use this kind of tricks during inference. We also added GitHub issues, and the way we concatenated them is like you have the title, then you have the comment, and then you have a token saying this is another comment, and then you have the other comment, etc. To kind of have some structure and just not blindly throw this data into your model. We did the same for git commits. So basically we have the file before the commit and the file after the commit and then the commit message. So for example, during inference, you can do this with starcoder. You can say commit before is the Fibonacci and the commit message is add type hints. And then after the commit after is kind of adds them. We did a lot of cleaning because apparently people don't try to commit messages. And then we also did Jupyter notebooks. We used the special formatting to kind of separate the code blocks from the markdown blocks from the output. And if you use the model during inference and you say this is some code and give me the output, it kind of acts like a Python interpreter and gives you the output because it did see them from notebooks, which is pretty cool. So yeah, that was what we did for data curation. If you wanna also have like, I don't know, you wanna train a code model and you have a data set, you're wondering which tools can I use to clean them. There's the datasets library from HuggingFace, which we also use for our filterings. You can use methods like map and filter and batch mapping to like use multiprocessing to clean these files in an efficient way. The last way is to tokenize your data. You can use HuggingFace tokenizers or use the tools given in frameworks like Megaton and LAM, which we use for our tokenization. And from the tokenizer, we just took a tokenizer like BPE, and we trained this on a lot of code, and then this is the tokenizer that we use for our training. So that was it for data. Now we'll see architecture. So the model is like a decoder style, like GPT-2, which is by 15 billion parameters. But we kind of did some changes which were motivated by the answers to this question: what do people want from code model? People want fast inference, so we chose 15 billion parameters. It is still a bit large, but like not very large. And it has some code optimizations in the transformers integration. Also, people want to have like cheap generations, especially when you increase the batch size. This is why we used multi-query attention. If you're wondering what that is, so basically in your transformers, you have like a lot of heads, and in the standard transformer, each head has its own keys and values. What multi-query attention suggests is to have the same set of queries and values in all the heads. And they found that this doesn't degrade performance. And it gives you like, you could, during inference, you could fit into your model much larger batches, and the inference is so much faster. And this is really important for code models. In our experiments, we found that it did give a performance degradation, but it wasn't very significant, and we thought it was a very nice feature, so we kept it. People also want long context, so we scaled our context to 8,000 tokens, and this was possible thanks to flash attention, otherwise the training would have been very slow. And the last thing is like, when you're editing your code, sometimes you want your model to use the context that's on the right. For example, you have a function that's already implemented, and you want to add a docstring. So to be able to do that, your model needs to know what's on the right. And if you just use a model like GPT-2, it can attend to context that's on the right. So a trick to do that is to use a technique by OpenAI called fill in the middle. What you do is you take your training data and you apply transformation, and that's all. And after that, your model will be able to see context on the right. And how does this work is that like you have a code file, and you kind of split it to three. So you have the prefix, which is the first part, the middle, and then the suffix. And during training, you swap the middle with the suffix, so that it's now prefix, middle, and then suffix. So your model can, prefix, suffix, and then middle. Model sees the end before seeing the middle. And you add some tokens to indicate to the model that it is in the fill in the middle mode. And so during inference, if you want to do that, you just need to swap the order and add those tokens, and the model will be able to predict what should go in the middle. So that was it for the architecture choices. Regarding the training setup, we trained on the HuggingFace cluster. It was 500 GPUs for 24 days. We used the Megaton LM for the training with the 3D parallelism, and we trained on 1 trillion tokens. So for that, we didn't have like, in our dataset when we tokenized it, it was 250 billion tokens. But if we trained only on that, our model would really be under-trained based on the scaling laws. So we did multiple epochs, meaning that our model saw the data multiple times. And we found that the loss just kept going down. We didn't overfit by doing this, which was great. It was kind of smooth sailing, like we didn't have to do like any manual intervention. I think the job restarted twice, but it was automatic on the cluster. So this is the family tree of the models, because we didn't just release one, we did release a lot. So this starcoder base, which is the base model trained on 1 trillion token from 80 plus programming languages. And then we took this model and we fine-tuned it more on Python, because people, for example, in data science, Python is very important. And we got starcoder, which has better performance on Python than starcoder base. It is still good at like multilingual. And we also train smaller versions, Starcoder, like 1 billion, 3 billion, 7 billion models are released. We also released Starchat Alpha, which is an instruction-tuned version. It can act as a chatbot because Starcoder base is just for code completion. And we also tried training Starcoder on like natural language, because in the beginning we only trained on Markdown and on code. And we were surprised that it was able to kind of generate like English text, which is normal about like cuisine. And apparently this was an HTML in Markdown. So we tried like fine-tuning it on more English text to see what we would get, and we got Starcoder Plus, and this was able, it made us like, we could build a better chatbot than Starchat Alpha based on Starcoder Plus because it has more natural language. So the BigCode family tree became a BigCode ecosystem, which is really heartwarming. Like you can see the impact of open source because we released our training data and we released our model. A lot of people just use the training data for their pre-trainings. For example, stable code, Codegen 2.5, Workplace, Decicoder. They all use Starcoder data for their pre-trainings. And then there's the community fine-tunings where people took Starcoder and they instruction tuned it to have like some chatbot-like versions like Wizard Coder, Tango Coder, and deepfake SQL coder. Yeah, so these are some of the models based on the BigCode ecosystem. Now let's see evaluation. So this is a table. So there is all the inside like the code llama models, which are like now the strongest open code models. But I'm going to show you that in another slide. And you can see that, like, for example, the models that were before, for example, Codegen, they have, so first, what is this benchmark? So how do we evaluate code models? We have some benchmarks where you have a function signature in a docstring, and you ask the model to complete the function. When the model completes it, you run this against unit tests, and then you see which solutions compile and which solutions don't run, and then you compute like what we call the pass-at-one score. So this is not like we do for NLP. For example, we use metrics like exact matching, like blue, and this doesn't work for code because you can, like, the space of the possible solutions is very large. Just think of how many ways you can sort your list. So it doesn't make sense to have a reference solution and exactly match against it. So using unit tests is like a very efficient way, but it's also challenging because you need to build that benchmark and you need to build the unit test for it. So Univa is kind of a popular benchmark now, although it's probably not the best because it only has 160 problems, which is very little. And yeah, so you can see that Starcoder 15B has a strong performance on that, and these are like the performance of some closed models. So Starcoder 15B is not just good in Python, but it's also good on a lot of other programming languages. This is like the BigCode leaderboard that you can go to and see the performance of all code models on more than 13 programming languages. And you can see, for example, here Wizard Coder and Octocoder, which are instruction-tuned versions of Starcoder, which kind of top the leaderboard on a lot of programming languages. But this space is moving super fast. Let's move for Starcoder. I think it's now over here because like a few weeks ago, Meta released Code Llama, which is a strong code generation model. They didn't do entirely the same approach as us. We started from scratch and we trained the code model. They started from Llama 2, and which is like the natural language model, and they further trained it on code. They trained it on 500 billion code tokens from GitHub, and this gave like a lot of performance boost because if you take the Llama 2, it's not very good at coding. But after this fine-tuning, it kind of gives strong performance. So that's also a good thing. For evaluation, we developed like a BigCode evaluation harness, which is a repository where you can evaluate your models on a lot of benchmarks, not just human eval. There's like, for example, DS1000, which is built on like Stack Overflow questions that they can be transformed into more complex benchmarks. And it has like, for example, 7 libraries. You can test the performance of your model on PyTorch, Matplotlib, NumPy, TensorFlow, and stuff like that. So it's kind of like unified framework for evaluation. And we also have like this leaderboard where we add, whenever there's a new model, we kind of add it so people can better choose which model they want on which programming language. So that was it for code evaluation. A lot of things can be improved, for example, now we're just testing how good models complete functions, but we could also test how well they complete classes. Try to also use the repo level context, which a lot of people would use, for example, in the VS Code extension. You don't want to just use the current context, but you also want to use context from neighboring files. But now there isn't really a benchmark to evaluate that. Even if you would train on it, it would be hard to understand if your model like to have a quantitative benchmark for evaluating them. So for the tools that we released with StarCoder, we have a VS Code extension that you can download at the market. It's called HuggingFace VS Code, and it also completes your code. And it also has a nice feature of like for code attribution. So if you enable this feature and the model generates code that was copied verbatim from the training data, it warns you. It tells you that this code was copied from the training data, and you can go to like this space stack search, and you can see which repositories came from. And this is great because even if you train on permissive licenses, you still have to do attribution if your model, if you generate something that is exactly the same. So that's one of our data governance tools. Other plugins we released are like Jupyter plugin. It's like a Chrome extension. If you use Jupyter there, you can have the StarCoder. There's also a Vim plugin, there's an Emacs plugin, and there's another VS Code in JetBrains plugins by Refact AI. So yeah, you can try these tools. The VS Code, for example, also has code Loubna now integrated, so you could try both models. Regarding the license of the models, they use OpenRailM, which is royalty-free. It also enables like downstream distribution of derivatives and commercial use. The only restrictions are like based on ethical. If you want to use, for example, the model for malware generation, you can do that. But other than that, you should be free to use the model. Yeah, one last thing I'm going to talk about that we get asked a lot is like how to deploy these models. So I'm not personally working on that, but I'm going to tell you how it's being done at HuggingFace. So the challenge is like the model size. The model is still large. Like if you really need like some GPUs to run it fast. For example, in the VS Code extension, it's being run on the GPUs with the library that I'm going to show you so that it is fast. But if you have to wait like 4 seconds for the generation, the tool is not really useful. So there are the HuggingFace inference endpoints where we take care of like the deployment and everything. You can just choose the model and give you an endpoint. There's like a free and also paid version for that. And then there's the text generation inference library, which is used by HuggingFace in production. This is how we serve models like Falcon, StarCoder, Llama, Galactica, PT, and other models. It has some nice features like tensor parallelism. It has like monitoring, token streaming. Yeah, and some other optimization. Basically, each architecture is further optimized so it runs faster. And it is also secure if you want to deploy it. So for example, to use TGI, it is more product focused, so we will need to have like an agreement with HuggingFace, but you can just look at the tool if you want to develop something that's similar. Some users of text generation inference are having chat, which is like it's a platform that with the UI like ChatGPT is for our chat models. There's the Open Assistant model. There's also called Llama 34B Instruct. We're also using it for the VS Code extension. The Open Assistant folks also use this for their deployment, and it's also on market. So this was a brief introduction to how we're deploying these models. There's also a solution if people want to deploy it, like for companies without having to fine-tune the model themselves and deploy it. There's like a solution called SafeCoder with like there's a HuggingFace team which takes care of fine-tuning and deploying it and gives you just the service as an end-to-end solution. So this was my presentation. I hope everything was clear, and if you have any questions, please ask me.
So how many examples in your benchmark for Python and other language you have, and how these examples was generated or maybe created manually?
Yeah, so BigCode didn't develop benchmarks ourselves, but we use, for example, HumanEval has 160. Okay, it's not enough, but like it's still correlated to how the model.
It's not 1,000.
No, it's 100. Yeah.
100. Okay.
But we also evaluate, for example, on DS1000, which has 1,000 solutions, 1,000 problems, and we try to have the model solve that. We also evaluate on MPPP, which has like 300 problems. So we kind of try to evaluate on as many benchmarks as we could, and if you check the paper, you can, for example, find the results for that. And that's actually a good thing. It's not enough to evaluate on one benchmark, you should try as many as you can to really understand how the model works.
So, and code for this benchmark, I mean, examples code was created manually, and verified it, and okay.
Yeah, there are teams who worked on that, like manually created them, had unit tests, and made sure that they kind of make sense. Yeah.
First of all, I want to thank you for the presentation. I have two questions. The first one is, how do you measure the quality of the code? Like, if the code runs, it's correct, but the problem is its length. How do you measure it?
You mean for training?
Yeah.
So for training, we did a lot of ablations where we tried to be a little bit clever about our filtering. So for example, we use techniques like computing the comment to code ratio. So we're wondering if some files have a lot of comments, they're probably better. But this didn't really boost performance a lot. It was like very marginal gain. It's hard to implement because you need to do it for each programming language, so we kind of dropped that filter. We also tried using stars. We tried only keeping repositories that had more than 5 stars, but we ended up dropping a lot of data that really made the performance much worse. So the only thing that's helped is like just removing duplicates, and the other filtering we did is to try to just remove files that have like very long lines that are more likely to be auto-generated. But other clever filterings didn't really improve performance, so we didn't use them.
And the follow-up question is, does the model try to prioritize code length? Does it try to be as short and as precise as possible with its answers?
You mean if you ask it to generate more, it's gonna be worse than No, we actually in the paper we found that because we have a long context, and we found that thanks to this long context, the model can attend to tokens that are much further, and it works because in attention, it doesn't. The model doesn't work bad if something is far. This is not how it works. It actually attends to tokens that are more correlated to what you want to generate, so it's not an issue.
Thank you for the great presentation. My question is more on the kind of future prospect side of the things. What about the processing of the output messages of the generated code, like the compilation errors and warnings, etc.? And more importantly, what about the debugging of the generated code, like an assistant in the debugging of the generated code?
You mean
in the context of the trained kind of data?
How we curated this for training?
No, I mean, when the code is generated, I try to compile it, I receive some error messages and etc. How can I, is it in the future? Maybe I will be able to receive some help and feedback based on the training data set, how to kind of fix that.
Yeah, I think for example...
And also the debugging later.
Yeah, maybe for that you're going to need a model that's instruction tuned so that you can ask it, because this model now does code generation, it completes your code. But I think, for example, if some people tried with a coder, which was instruction tuned, you can give it some stack traces and can try to find the error and fix it. Maybe it's because we trained on GitHub issues, and sometimes there are stack traces and errors, so it could work on that. In the future, we're going to try to train also on PR reviews, so this could probably also help improve this capacity.
Hi, so thanks for the presentation. I had a question regarding the extension. So let's say you have a function which uses dependencies from other files in your project. How do you compile the prompts to the model?
Yeah, that's a good question. Currently, the function only uses the file that's open, so we don't use the context from the other files. But like in the next iteration, we're gonna try to use the context in a more clever way, because now we just take random sequences and we concatenate them, and so there isn't really a repo level structure in the context. So we'll have a next BigCode iteration, and we're gonna try to have that repo level context. And in the VS Code extension, we could probably see which files are open or which files are important, and try to add them into the context. But now it's not using the extension.
Yeah. Thank you. My question is about fine-tuning. What's the promise of fine-tuning? And we saw like a 20% raise after fine-tuning your base model. How far it can get? What's the balance between the quality of the base model and the fine-tuned models for code?
Yeah, I think having a good base model is very important, because I think, for example, for code gen, people try to fine-tune instruction tuning and they didn't get as much boost. When they tried with star coder, they got more, and then when they tried, for example, now with code Llama, they got even more better fine-tuning performance. So yeah, having base model is important. So you should try to take the best base model for your programming language, and then curate fine-tuning.
My question is kind of about what's your intuition about how far the only fine-tune can boost the base model, like the numbers here. What's your intuition?
Yeah, I think we can see, for example, these models that are released. I feel like the community is really trying to max out how much you can improve these models. So, for example, now I think there's a wizard code model based on code Llama, which has I think 70% plus at one on Python. Maybe they could add a few percent more, but yeah, that feels like maybe that's what one can do.
First of all, thank you for your talk. I have a question more on the closed versus open source approach. And I noticed that there's some things that HuggingFace is doing to prevent negative use cases or ill-advised use cases for fine-tuned models downstream. But how do we balance the benefits of open source, namely that you get a big community, you can have faster iteration, more buy-in from people, with some of the negative, potential use cases of just releasing such a powerful model that other people can fine-tune for malware?
Yeah, I think there are like some risks with just having models open like that, but I think the solution is not to have models that's closed. I think that's just like a pretext for not releasing these models. There are things you can put in place in still like open source models. For example, for the instruction-tuned versions, you can try to use Error check to have models that are less toxic, less biased. You could also have, for example, the open array license where you can choose these models for malware generation, for dissemination, stuff like that. In your training, you could try to remove personal identifiable information like we did. You could also have code attribution tools to improve data governance, but the solution is not to close access to these models.
Yeah. Thank you.
Hi. So when you talked about removing generated code from the training data set, what was the reasoning behind it? Was it like that the output of the model would look like non-mind readable, or like in some sense maybe it's better in terms to add more generated code? Maybe it will solve more problems.
I see. Okay. By auto-generated, I don't mean, for example, code that was generated by GitHub Copilot, because we don't. It's very good. You can say there's no way to filter that. I mean, it's things that were generated by bots or something like that. When you look at them, they're basically garbage. It was more this type of auto-generated that we were trying to filter. For example, one Python file, which is like, it is one line, it is very long. There's no way this is useful for the model. So these are the kind of things we're trying to remove, but like code that looks good, like a human would like write it, we don't have any filter for that.
I meant that code that doesn't include, like visually, like variable names are like one symbols or something like that, but it's correct, it works, and maybe it will improve the performance of like correctness of the output in terms of like correct code. Maybe not readable code, but correct code. So maybe it will help that.
Yeah, so the auto-generated files that we removed, I think they mostly don't compile. It was really like this type of, but those, for example, those that you said, I think there's a problem.
Sorry, can I have one more question, please? What's your opinion about the polymorphic malware written with LLMs? So you have a nice small LLM that can generate code, and it can be, for example, instruction tuned for finding its own weaknesses and vulnerabilities and modify the code. So in the past, making polymorphic malware was a difficult process, but now with LLMs it got much easier. So even if I'm right, in April there were several articles about polymorphic malware generated with calls to the LLM API. So as the models become cheaper and smaller, it's becoming more and more feasible.
Yeah, I think from a security research point of view, it's really very interesting to kind of investigate that. For example, when we were compiling datasets, there was like a big debate: do we keep like malware code? Because if you go to the dataset on the hub, it's kind of flagged says this dataset has malware. So there was a big debate: do we leave it or not? And there was some security researchers saying this code is already out there. If someone wants to fine-tune your model on that, they can just keep it there so the model can learn. In the end, we dropped it because of some data governance issues. But I think it's also interesting to kind of investigate. If someone does that just for the purpose of generating malware, they would have some issues with like the license. But as long as it is for research, I think there are some security researchers trying to do that. It should be fine to do that with the model.
I think the license is kind of not stopping the people who
Yeah,
generate
for
malware.
sure. Yeah, but like you do your best to kind of.
Thank you.
You said that like Llama coder, the new model is based on the just LLM model for like, generating the natural language. And why you started from scratch your own model and not from the like, open source LLM for natural language?
I think for two reasons. First, you need to have a good base model to start from. At the time, there was no Llama 2 model. And also, I think our model was more focused on code completion. If, for example, you use the Llama 2 model, we would have to follow all the restrictions that come with it. For example, the fact that they didn't say anything about like the training data. So we're trying to have this transparency. We can do that like top of a model that doesn't have that from the first point. You would also have to follow the license. I think in Llama 2 you can choose the outputs for commercial use, while with our model you can. And so yeah, that's one of like the reasons why we will start from scratch and to have something just go through that.
But do you plan to research when there will be a good model to scratch to start from?
Yeah, maybe we're gonna turn around. I think now we're still like going the starting from training from scratch direction. We think we can have like more performance. There are a lot of things we can do better. We can like add more recent data and also try to have this repo level context. You would probably have the model much more, train also longer. So even starting from scratch, you could like get a lot of performance improvements with that. Yeah.
You mentioned a couple of times the duplication of data sets. I was wondering if you use Google's open source project for the duplication, or you guys had your own.
Yeah.
And also, if you could give us a simple example of what would an original data set and the duplication would look like, because there was two famous downsides of data.
Yeah. So we had our own pipeline because we used it before for like some small code parts experiments, and we kind of scaled it to do that on like the full data sets. But like for example, this method of like mean hash plus LSH already exists in literature. There are like a lot of other people using it. I guess for example the Falcon model, they also used this duplication technique. But we have our own code. At first we were just like running it in a distributed way on like a lot of CPU machines. Now we have like a Spark implementation. And it's open source, you can find it like in the BigCode project. And for your second part, were you like talking about this compute part or?
I mean, just a simple example of what would the original data and the duplicated one would look like.
The size. So the original data set, the stack is like 6 terabytes. After the duplication, it becomes 2.9. So you remove almost half of the data after you do the duplication. And you still get better performance than if you were to train on the original data.
You got any inference on comparison?
Yeah, so when we were like integrated the model transformers, we did like measure like the latency and focus on and try to do some optimizations to kind of improve it. And then after the integration in like text generation inference, so they have like monitoring tools to kind of like see what latency the model has. If like we need more GPUs since it is being served in like a BigCode extension. So yeah, there are like some
So is your model like faster than other public models?
I think if you go to the leaderboard, you can measure the throughputs. Yeah, so this is the throughputs. For example, if you see the code Llama version B, yeah, it has 25 tokens per second. This hardcoder has 43.9, so it is more optimized.
Thank you.
I was wondering if you do this filtering before training, right? But is there a way to also have it in during runtime, some code verification, like either syntax checking or compilation or something? Just to use something like this, or is it on the roadmap?
Yeah, I think for example in the VS Code extension for GitHub Copilot, they do that. For example, when the model generates something, you could try to see like the logist probabilities and remove those that are less likely so that the model doesn't count as garbage. You could also, try, when the model wants to generate something, you could check these probabilities and only output something which makes sense so that the user doesn't often get these kind of nonsense generations. I think they also try to build the AST of like the generation to see, for example, if the function is complete. So there are some techniques like that. In the one we open source, we didn't like do post-processing for that, but it's open source if people want to open the large features, they can. So it's not really product focused.
First, thank you for the talk. I was last year on the Andros talk, and back then this project was in the initial phases, and the progress is really remarkable. My question is more on the financial economic part of this model creation. You mentioned 500 and 12 GPUs that you use for training. I guess you mentioned also like for how long you train the model, but I think that 24 days. Yeah. So the question is basically how much does it cost one training to have one training, and since you cannot just train once and consider your work done, basically you have iterations, etc. How you control the budget?
Yeah. Yeah, so I don't have like the exact amount, but like it can go from like hundreds of thousands to millions of dollars for like these kind of trainings.
For what?
Yeah. And yeah, for models that are in that range. And yeah, so if you want to train the like iterate and fine tune the model, reiterating the model, you're gonna have to train from scratch again. So for example, the next BigCode iteration, it's gonna be like phases. So like now in the last 8 months we started there, we're working again to release a new model. So yeah, we're gonna have to spend something like that's comparable to get something that's like a really stronger base model. Other than that, you can just do like small fine tunings. But yeah, you would have to spend something like that whenever you want to get a stronger base model. For example, I think in Meta they did like an easier approach where they took Loubna tool for which they slowly spent a lot of compute and they kind of continued training on code, so it was cheaper than like starting from scratch. So that's also another way to do this kind of thing. But you will always need to have a base model a good base model to start from, and someone needs to train that base model. So yeah, this is what we're trying to do, and then the community can just do small fine tunings on a few GPUs.
I have a question about names of variables and function names. For example, we have a bubble sort algorithm that published it a million times and indexed it also, but in most cases they use A and B variable name, and you write, for example, Alice and Bob instead. Will this your algorithm recommend to rename to A and B because this is most popular, or just doesn't care because understand that this is not meaningful?
Yeah, I think if there's like a tendency to some, like a pattern to have like some variable names, the model is probably more likely to output these names, but if you change it, it shouldn't impact like the quality. I think the model is supposed to be good enough to understand that like changing the variable names. If that's an issue, we'll probably have bigger problems.
Does code vectorization differ much from vectorization?
Do you mean if you want to like induce embeddings?
Yes.
I think now we're treating the problem like just text problem. This is how we're doing the training. If you want to, for example, compute embeddings, encoder models are much better at embedding than decoder models. So we trained a BERT-like model, but for code. It's called star encoder. We did that mainly because we needed the designated entity recognition model to remove PII. So we also released this star encoder model that you can use to compute embeddings if you want, inside the same way as it works.
Did you hear about the Gorilla model that uses APIs through the text calls, that converts text calls to API calls, with text queries with the accurate API calls?
Yeah.
I guess Microsoft released that. So I think it's a big issue, the correct API calls with not hallucinating parameters and so on. And the small models that trained only or fine-tuned heavily on the API calls, like hundreds or thousands of them, is very useful, especially in the HuggingFace ecosystem when I forgot the model name that uses the HuggingFace ecosystem, like tools to solve other problems. Yeah. So I want to plan like work in that direction, narrow API knowing LLMs.
Okay, yeah, that's a good point. Yeah, some models sometimes just hallucinate the APIs that don't exist and try to incorporate just in the code crash. So it's probably gonna need for some fine tuning to have them work on that. Some people are trying to use reinforcement learning to kind of have start things work. So there's the TRL that Ms. is working on. They have like now a text environment tool where you can, for example, force your model to act like as a Python calculator or something like that. So that could be a direction for trying to fix those hallucinations and have models for these APIs. But yeah, it's still very early research and all that.
Because these models, they can code the bubble sort, but bubble sort is actually not what we need in production. We need the accurate API code with all correct parameters.
Another thing you could do is actually add documentation in the context. Is, for example, you do some retrieval to retrieve like the documentation of the API that you want, and you add it to the context, and then you ask the model to generate something in that API that you want.
Maybe, but we are facing, now we are facing retrieval problems with rankings and so on.
Yeah, that would be less expensive.
You said you did multiple versions of the stakeholder.
I'm sorry?
Multiple version of staff order with different number of parameters.
Was it the distillation or just from scratch?
No, we trained this from scratch. Because this is before wanted like this. You could do distillation, but then you might get some performance degradation. We had some compute left, and it is like less expensive to train these smaller models. So we just trained the smaller versions in case people want to use them, and then they can use them to even quantize them more.
I had about discussion in a community right now about this ethical question that people should know which content was generated by LLMs and which content which written by humans. And what about the code? Is it possible somehow to detect which code was generated by LLMs and which code was?
I think now I'm not really aware of something like that to find it. See, I think OpenAI is trying to work on watermarking, constructed their generation, but I think probably there isn't really like now solution for that. Yeah.
One more small question about the architecture. You mentioned the training, the fill in the middle training, how do you call it?
Yeah, filling in the middle to have
that technique. Basically, you said for that you reshuffle your code with suffix, then prefix, and then somehow prompt it that now it's generating the middle. Why isn't that done with just mask without reshuffling? You basically can mask the middle part and.
Yeah, but then for that you will have to change your objectives as well, how you train the model. For example, that's what's being done in encoders. But with this approach, we don't change anything in the law. It's the same function, the same training. Just that when you prepare the data, you kind of like take your code, you swap and you add tokens. And the OpenAI paper that developed this, they found that it works much better than if you were to follow these approaches, because it doesn't impact the left-right prediction. The model is just as good as if we didn't train without it. Well, there's a small performance degradation, but it's still like a good approach. The model can do it filling without getting bad at those other tasks. Are there any other questions? Well, thanks everyone.